Hi, I am Olga. I work for Microsoft. Today, I would like to present our work on proactive resume and pause of resources for Azure SQL database serverless. We have analyzed hundreds of thousands of serverless databases worldwide and concluded that many of them have a predictable resource usage pattern. For example, this database is active during a very short period of time at the same time during the day, and it's idle otherwise. We want to leverage such predictable patterns to allocate resources if and only if they are used by the customers. In this way, we make sure that we guarantee high quality of service to the customers and avoid wasting resources. The current reactive resource allocation policy deactivates the resources that were idle for a while. Unfortunately, when the customer comes online after idle time interval, there is a brief time interval during which resources are unavailable. Even if this time interval is only a few minutes, it can be problematic for latency-sensitive applications. Our goal in this project is to predict the login pattern for each database and proactively resume resources few minutes ahead of predicted customer activity, such that when the customer comes online, resources are already available and high quality of service is guaranteed. We also want to deactivate resources that are idle. Unfortunately, idle time is very fragmented. 72% of idle intervals are very short, they are within 1 hour. They contribute only 5% to the total idle time duration. We want to avoid pausing resources for such short idle intervals to relieve the backend from the overhead of frequent scaling operations. The current reactive policy logically pauses a database that becomes idle. During logical pause, resources are still available, but customers are not billed. Thanks to logical pauses, 60% of pause and resumes workflows are avoided. But on the downside, resources often stay idle during logical pauses, and cogs are wasted. Also, if the customer does not come online during logical pause, we physically pause the database. We can reclaim the resources during physical pause and reuse them for other databases on the same node. Unfortunately, the duration of physical pause can be too short to effectively reuse these resources. Therefore, we propose to predict the login pattern for each database, and if we know that the next login is very far out, we can skip logical pause and go into physical pause immediately. In this way, we make the time intervals during which resources can be reused longer. So we can summarize the current reactive resource allocation policy as a finite state automaton. When the customer becomes idle, resources are logically paused. During logical pauses, resources are available, but customers are not billed. If the database stays idle during logical pause, we physically pause the resources. If during logical or physical pause, customer comes back online, we activate the resources. Now we want to avoid the disadvantages of the reactive policy and convert it to proactive policy as follows. So when the database becomes idle, we predict the next login time. And if we know that it's going to be within the next few hours, we logically pause the database to avoid the overhead of frequent scaling operations. On the other hand, if we know that no login is expected within the next few hours, we go directly into physical pause, and we reclaim resources and reuse them for other databases on the same node. If we know that a physically paused database is about to receive a login, we proactively put the resources into logical pause and wait for customer activity. After logical pause, we predict the next login again, and if we know that it's going to be far out, we physically pause the database. As you can imagine, implementing this proactive resource allocation policy for Azure SQL database serverless is very challenging. First of all, there are multiple configuration knobs of resource governance. Therefore, we need an infrastructure that automates knob tuning. It must have no human in the loop. There are millions of serverless databases, and each of them has a unique resource usage pattern. Therefore, the infrastructure must be scalable and lightweight. And proactive resource allocation decisions must be customized for each database. Azure SQL database has very high availability and durability requirements. Therefore, the infrastructure must be distributed. It must have no single point of failure, no dependency on external components, And it must be seamlessly integrated into Azure SQL ecosystem and reuse its existing components. We have built such an infrastructure and consists of the online and offline components. The online components track the customer activity and compactly store this history in a database history store. Based on this history, we predict the next activity for each database. We store the login time for each database in a metadata store. Based on this metadata, we trigger the resource allocation mechanisms ahead of predicted customer activity. We reuse existing diagnostic and mitigation runner and incident management to handle any incidents in production. The offline components analyze the long-term telemetry and compute the KPI metrics. These metrics are visualized via an interactive dashboard, and if the accuracy drops, there is a retraining components which resets the configuration knobs of the online components. I will briefly summarize the main components of this infrastructure. So the database history store must be durable. It must survive the move to another node or another elastic pool. It must reuse the existing backup and restore mechanisms since we don't want to re-implement them. It must be efficient. It must store only relevant recent history per database in a machine-readable format. And it must be precise because activity is predicted based on login timestamps. To satisfy all of these requirements, we have decided to store database history in a machine-readable format in an internal table within the database itself. The internal table is called POS-resume history and it stores two columns, the timestamp and the event type in an integer format. The timestamp corresponds to the epoch time, which is the number of seconds since January 1st, 1970. And the event type can be either 0, physical pause, 1, logical pause, and 2 is a login. We have decided to store this history in an integer format because it's much easier to operate on integers rather than date type and strings. Going forward, we will convert this history in a human-readable format and make this history available to the customer. Based on this history, we predict the next activity as follows. So assume we want to know when the customer will log in on day 6. We will look back several days. In this example, we look 5 days back. And we will slide the time window. During each time window, we compute the probability of login as the number of days on which we have seen a login during this window divided by the total number of days in history. In this example, the gray points represents the login. So we have seen a login during 4 days. 4 divided by 5 days total is 0.8. And if this probability exceeds the confidence threshold, we will recommend to proactively resume the database ahead of predicted start of predicted activity. Start of predicted activity corresponds to the first login we have seen during the window. And we will keep resources up until the end of predicted activity, which is the last timestamp of the login we have seen during the window. There are 4 possible proactive resource allocation decisions. If the next predicted activity is known to be close, we will logically pause the database to avoid the overhead of frequent scaling operations. If the next predicted activity is far, we physically pause the database to avoid wasting cogs during logical pauses. If next predicted activity is unknown and database is young, there is not enough history to make a reliable load prediction. Therefore, we default to the reactive policy and logically pause the database. And lastly, if the next predicted activity is unknown and the database is old, we assume that this database is idle most of the time and we physically pause the database to reuse the resources. So we have analyzed the impact of this proactive policy. We evaluated 4 largest Azure regions. 2 of them are in US and 2 are in Europe. More than hundreds of thousands of serverless databases are currently deployed in these regions. We evaluate the quality of service as the percentage of first logins after idle intervals that happen during time intervals when resources are available. We evaluate the operational costs as the percentage of time resources stay idle and cogs are wasted. And we evaluate the overhead as the size of database history and the latency of activity prediction and proactive activation. So reactive policy logically pauses a database that becomes idle. Thanks to logical pauses, 60% of first logins after idle intervals happen during time interval when resources are available. The proactive policy is able to bump this percentage to 86, thanks to a proactive resume, ahead of predicted customer activity. And we observe the same trend in other regions. On the downside, the idle time becomes slightly higher. Remember that reactive policy logically pauses a database that becomes idle. Therefore, the total idle time is about 6% of the total time. Given that proactive policy skips some of the logical pauses, the idle time due to logical pause goes down to 4%. However, proactive resume also contributes idle time, because in some of the cases, the proactive resume will be wrong, the customer did not come online. Because of wrong proactive resumes, about 1% of the time resources stay idle. Even if proactive resume was correct, some idle time will be added because the proactively resumed resources are not used instantaneously, but only when the customer comes online and uses them. Therefore, overall, the idle time goes up from 6% to 7%. And we observe very similar trend in other regions. Only in East US 1, the idle time actually went down, but it's more of an exception. We have observed very similar trends on other days of the week. The database history store stays within a few kilobytes for each database, and the latency of activity prediction stays within a few seconds for each database. Therefore, we conclude that our solution is accurate since over 80% of first logins are predictable. It is efficient since the total idle time is increased only slightly, and it is lightweight since history size is within a few kilobytes and latency is within a few seconds. We are currently rolling out this solution worldwide. We are aware of several limitations and we are working on solving them. Thanks.